Hey everyone, Elmonius here. Back at it again with another upload. 3 months later. Anyway, okay, so here's an integral. Well, I've got two problems actually. Got two integrals. One's just the squared integrand, the other one. And integrals of the Bessel function, modified Bessel function of the second kind. It's uh, it's the Bessel function that satisfies the Bessel second equation. So I'll leave a link in the description below for more information on it. It's going to be a link to the Wikipedia page and the MathWorld page. Anyway, so I'm also going to just preface throughout the video. I'm going to solve the first one in red and the second one in blue. So just when you're scrolling through the video, you're going to know it's the second one when it's being solved in blue. All right. So let's begin with the first one. So right now, we're going to use a theorem that Glasser came up with, where the integral from 0 to infinity for f times g is equal to the integral from 0 to infinity for the Laplace transform of f times the inverse Laplace transform of g. So we're going to apply that to the definition of the modified Bessel function of the second kind. So, and this would look like this. So what's going to happen is you're going to take the Laplace transform of the cosine and then the inverse Laplace transform of 1 on root t squared plus 1. And by doing that, we get this. So the 1 on root t squared plus 1, 1 on root s squared plus 1, right here, because in the frequency domain, I think that's called, that's going to turn into j sub naught. And then the cosine is pretty basic. It's going to turn to u on u squared plus x squared. Factor on x squared from the denominator, just to simplify it a little bit. So now we have this. So we have this right here. And what we're going to do is we're going to integrate both sides of the equation from 0 to infinity. And by doing that, we get this double integral. And then we're going to factor out the v on v squared plus 1 and then just integrate with respect to x. And the integral from 0 to infinity for j sub naught is 1. And then after performing the u sub, u equals vx, we get 1 on v for this integral on the inside. And so then that's going to cancel with the v right here, which is very nice, and then we get pi on 2. So that's the first. It's the first evaluation. Pretty simple. Now, time for the second one. So here's the second one. So we're going to use, for the second one, we're going to use the theorem that Ramanujan came up with, and a bit of a corollary to that. So here's the theorem that Ramanujan came up with. It's yeah. So I'll call this like a cosine transform. So the cosine transform of a cosine transform is equal to pi over 2 times the function that you start off with. That's basically what it is. And so then I'll leave this to the viewer to come up with this. It's pretty simple. Okay. So now we're going to let f of x equal k sub naught, and then g of x also equal k sub naught. So f of x equals g of x at the end of the day. So to find this, we're going to use the first one. So we're going back to this cosine definition. And so if you look over here, we're going to put this down here, and then this down here. And then we get this. So now we know the cosine transform of k sub naught is equal to pi on 2 times 1 on x root x squared plus 1. And so then we have this. Now all we have to do is plug it in. And so these two of these 2 on pi and pi on 2 going to cancel out. We can simplify these pretty easily. Just turns into 1 on x squared plus 1. And then once again, that's the same integral that we had from the other problem, which is going to simplify down to pi squared on 4, which is pretty nice. So that's about it. Yeah. So what we can say is that the integral for this function, for this weird, bizarre function squared, is equal to the integral of that function quantity squared. Which is, it's a very strange property that does not exist for most functions. So, hope you enjoyed. Thanks for watching. I'll see you in the next one.